to run a Monte Carlo simulation in basic risk factors and then not reprice the positions, but just approximate it with deltas and gammas. You have to be very careful when you do that. Suppose you have an exotic, suppose you have, let's call it a range accrual. Have you ever heard of an instrument which is called a range accrual bond? Okay. A range accrual bond is a very funny thing. A range accrual bond gives you an accrual, the coupon accrues for each day that the fixing of the interest rate, say Euribor for that day, falls within a range. So, and these were very fashionable, say 5 or 10 years ago, at which point also the interest rates had the floor at 0. So they had, an upper limit, and they said, if the interest rate fixing is above 5%, you get a coupon of, say, 6%, accrued for that day. I'm sorry if it's below. If it's above, you're screwed. You don't get anything. Now this appears very, very attractive to investors. It appears. Why? Because generally, those coupons that accrued and those strikes were quite large. So maybe a plain vanilla bond, risk-free, would give you, say, 3%. A range accrual bond would say, well, for every day that the interest rate is above 6%, below 6%, you get a 5% coupon. So 5% versus 3%. Interest rates are 3%. So, it looks like a good deal. The problem is the following. If interest rates are going up, then you're hit in both ways. Your coupon starts to reduce and may go to 0. And at the same time, the time value of money becomes very big. Coupons go to 0 when you most want them. When do you want to receive coupons? When interest rates are high. So the thing is, this seemed like a very, very attractive proposition as long as things go right. If things start going wrong, this can turn very bad very fast. This has a very peculiar sensitivity, with respect to interest rates. But in general, you could, if you had just this position, you could approximate it with gammas and deltas and maybe a higher order derivative. And if you run a Monte Carlo to try to, find the future development of this, to avoid repricing this entire beast, because pricing this beast is quite tricky, it's quite difficult. Okay? So if you were, say, a buy side, if you were long this, you could find your risk pretty accurately by running a Monte Carlo and without repricing, just doing first order, second order approximation. Think of another tricky situation. You are not an end user of this. Okay? You are an issuer of this. And generally, what did issuers of this thing do? They would offer this, keeping a pretty good commission fee for themselves, and then hedge the underlying interest rate exposures in the interest rate swap market, in easier instruments. And how would they hedge it? By finding gammas and deltas. So, if you run a Monte Carlo of your entire portfolio, whereby you approximate this, your issue, the same way you approximate it in order to hedge it, then you have hard-coded a var of what in your calculation? You have hard-coded a var of 0. Basically, what did I just do? Is I I built a Monte Carlo whereby this is, by construction, this. Because when instead of repricing in every scenario, I just say, well, I'll approximate it with a delta and gamma hedge. But what was my actual hedge? My delta and gamma hedge. So I approximate it the same way I hedge it. I hard code essentially a value at risk of 0, and my calculation is entirely useless. Basically, I have 0 resolving power. So that's what I'm saying. When you run Monte Carlo together with approximations, you have to exercise caution. We'll see later, another area where we have to exercise caution, which is closer to our stuff. Now, Monte Carlo advantages. Great many number of simulations. Many times than any kind of meaningful historical simulation. Okay. Very dark corners of probability space. I could actually, given enough computing power, I could actually look into products and into scenarios that are very, very, very improbable to happen. Another instrument, at the same time that the range accruals were very fashionable, was a derivative instrument built for banks, which said the following. You are the end user. You'll get a very, very large coupon as a reward. Suppose you have a plain vanilla IRS whereby you would get, say, 2% and you would give LIBOR. In these products, you would get 10%, not 2%. But on the other side, you wouldn't give LIBOR. You would give nothing, which made it even more attractive. You get 10%, you give nothing, except if fixings would say they would go below 2%, okay, you would reprice this every fixing date, every say quarter or every month, and you would pay, say, %2 plus you pay 2% plus previous coupon, and the first time this happened, you would pay 2% minus LIBOR. So think about, if everything is about 2%, okay, nobody's worried. As soon as you go to 2, things start hovering around 2%, nobody's worried. Suddenly you get a fixing at 0.5%. Okay? You got this one fixing of 0.5%, then what happens? You pay out 0.5%. You're going to say big deal, you're getting 10. But what's going to happen in the next fixing? You pay out 2.5%. What's going to happen in the next fixing? You pay out 4.5%.
What for?
What do you mean what for?
Why for?
Why do you do this?
2.5 again.
So, this has the profile of an insurance policy. Suppose you get a very high insurance premium to insure against a risk which is remote. At that time, these were very remote levels, very low levels of interest rates. But if this risk happens, it has a catastrophic impact.
And this is every 15 days? What do you say?
These were instruments that would go on for decades. So you would get things like that. So Monte Carlo simulation allows you to probe very, very dark corners of probability space. what are really the chances of this happening? Okay? If it happens, what's going to happen with the role of the coupons? These things, again, they used to be quite popular. They're not used by anyone right now. But that's the idea of a Monte Carlo. It allows you to find very, very remote possibilities and just focus on them. Increased accuracy. I can get inside of my risks, far outside the linear regime. Very important, because with these products, you could say, okay, what is my 97% probability of loss, my 97% confidence level? And you would go, this might have a profile like this, and you would go to here, and you would say, well, to 97% I'm fine. You go to the management, and they say fine. The thing is, you didn't realize that there was a remote chance, sometimes well below 1%, of catastrophic losses. Monte Carlo helps you focus on these kinds of simulations. Also, can tackle problems where the analytical solution is very hard or even impossible, and it can also give you information of how you get to a final state, not just what your final state looks like. Such a problem, barrier options. Barrier options are options. Imagine I have a call option on the stock, on the share of, say, National Bank of Greece. Say spot price is 10. I have a call option for 1 year at 13, which will activate only if within the period of that 1 year, the price of National Bank of Greece will have exceeded 15. These things do exist.
Can you repeat that?
I have a call option. Spot price is 10. Strike price is 12. This will, a plain vanilla call option would just tell me that as long as the price is below 12, there is no payout. If it goes to 12.5, I get 0.5. It goes to 14, I get 2. It goes to 15, I get 3. There is a variation of this called the barrier option. I say, exact same payoff, but for the option to be active in the end, I will need the price of the stock to reach at least 15 at some point during that 1 year.
So this won't let me exercise if the price is below 15.
If the price never reaches 15,
I cannot exercise.
I cannot exercise. If the price reaches 16 and then it goes to 12.5, I still get my 0.5. Whereas obviously if I had a binary option which it had to be 16 at the end, I wouldn't get my 0.5.
Throughout the life of the option.
Throughout the life. So this is the so-called path-dependent option. Path-dependent options are notoriously hard to calculate analytically. The calculation of this is much, much harder than the bracket shows. There are path-dependent options that are flat out impossible to calculate analytically. On the other hand, if I have a Monte Carlo of the asset dynamics that I would have used to price the plain vanilla option, I can get an accurate price of a path-dependent option. Again, this is more or less of academic value to us here because it's not a course on exotic derivatives, but it's a good thing. It's kind of a foolproof method. Given enough computing power, I can relatively easily value derivatives that are extremely hard or impossible to value analytically. At some point, there were some other products that were called the so-called mountain options. And they're pretty popular in Greece also. They wouldn't call them mountain options. They were packaged in structured mutual funds basically tracked a basket of indices or a basket of shares, and they said, for these shares, I'll track them for 20 years. Okay? The first year, the first share, the best one, it may be that all 40 of them lose money.
We don't have an average. I mean,
No, they were much more complex than that. They said, the first one, the best one, I will assume it has a return of, say, 6%, or its actual return, whichever is best. And then I lock it. The share has 6% return, that's it. Now I have 39 shares. The second year, the best one, I'll take it, I'll put it in a 6% return, or whichever is, or the actual return, whichever is best, I lock it. And I will go on for like this for 20 years. And in the end, I had 20 locked shares and 20 not locked shares, obviously the bad ones. I take the return of everything, and this is the total return of the mutual fund. Actually, these mutual funds, they made money. So no, people didn't lose money on those.
The return on the unlocked shares was the one at the maturity?
Yeah, yes. The thing is, the trick was the following. These things, essentially, they take the good shares and choke them. It sounded like free money. Why? Because essentially what you have there is a play on the bottom half of a basket of shares. You know, you take the good ones, you lock them at 6%, you know, and then you let the bottom half just play up as it is, play out as it is. Even for the trained person, it's very hard to have an intuitive feeling of what is the expected return of the bottom quantile of an index of shares. It's very hard, and the answer is very counterintuitive. It can go much lower than we think. On the other hand, to value this, you realize you have a very complex, you have a basket, you have selection rule, it's a pretty complex beast. This thing has no analytical solution whatsoever. You go to Monte Carlo space, and it becomes, if not exactly trivial, it becomes pretty tractable. Because what do you have? You start with a Monte Carlo simulation of 40 shares. You get their variance covariance matrix, and you got paths of, this would be priced every year or so, of 20 nodes each. At the end of each node, you would have a vector of 40 returns. Okay? And then, as you have those vectors, you would apply the selection rules and come up with an end result. You would repeat this many, many times, you'd get a price. Of course, putting in correlations was a little tricky, but in principle, you had a way to evaluate this. Without Monte Carlo, you have absolutely no way to do that.
Δεν καταλάβαμε ποιο τρόπο το κλειδώνουμε που είπατε πριν, συγγνώμη.
Το κλειδώνουμε. We say, give me the best one. Okay, the best one, I take it out of the basket, and I assume it has a 6% return.
Πώς το υποθέτω?
Δεν το υποθέτω. Εγώ σου κάνω ένα συμβόλαιο στο οποίο λέω θα πάρεις ένα ποσό στο τέλος. Αυτό το ποσό θα βγει με αυτόν τον τρόπο. Θα πάρεις 40 μετοχές. Κάθε χρόνο θα κοιτάω ποια είναι η καλύτερη. Θα τη βγάζω από το καλάθι και θα υποθέτω ότι έχει 6% return. Τον επόμενο χρόνο. Ποια έμεινε, θα τη βγάλω από το καλάθι και θα υποθέσω ότι έχει 6% return. Τον επόμενο. Θα πάει έτσι.
Υπάρχει περίπτωση στον επόμενο χρόνο να αυξηθεί η τιμή της μετοχής την οποία έχουν κάνει λόγο στο προηγούμενο?
Ναι, βεβαίως.
Οπότε χάνουμε.
Σε αυτή την περίπτωση θα χάνουμε. Αλλά υπάρχει και πιθανότητα η καλύτερη μετοχή να ήταν στο μείον 7%. Και εγώ στη βάζω στο συν 6. To make this even harder, there are cases where the issuer has the option of returning you your money plus interest at any time. Then it becomes very, very hard, even for Monte Carlo. Because then it's not just path dependent, the end result, it's also strategy dependent. I am the issuer, I have to devise the optimal strategy. This is probably in Duffy's book, that you mentioned. Could go like this. So, Monte Carlo disadvantages. CPU intensive. You need computers. You need big computers, fast computers. Okay. Another Monte Carlo disadvantage. We're introducing Monte Carlo. It cannot reproduce dynamics outside what I have put in. I'm saying I'm using loosely the term variance covariance matrix because I may have dynamics which are not normal or log normal. I may have dynamics of copulus, we mentioned copulus this time. I may have dynamics of the student T distribution. The thing is though, Monte Carlo will follow the dynamics I impose. Historical simulation doesn't. So this is one up that historical simulation has against Monte Carlo. Finite number of simulation systematic error. It's this, what we've seen. And similar to what we said about the range accrual, it can be very tricky if I want to compare things in Monte Carlo. Okay? If I want to compare things in Monte Carlo, it could be that the scenario, the difference I'm looking for is similar, is comparable to the actual, the actual number I'm looking for is comparable to the error I have introduced in my calculation. A very common error like this is suppose, for example, I want to find, say, the distribution of the difference of the prices between, I want to find the expected value of the difference of the prices between two shares, NBG and Eurobank, for example. And suppose, for some reason, I want to use Monte Carlo to do that. And I have a distribution of Eurobank, distribution of NBG, I take their means and compare them. And suppose that I'm really not careful, and I use two different sets of Monte Carlo random numbers. Okay? Then what's going to happen? One of them is going to have an error, the other one is going to have an error. I chose two kind of correlated things in this case. I expect their difference to be very small. However, it could be that the errors in each, they are comparable or larger to the difference. So I get nonsense. What I'm measuring is really systematic error between two different Monte Carlo distributions. I could generate a difference between NBG and NBG if I have two different.
So I introduced something like error in the correlation of the errors, the error term.
No, it's actually exactly the opposite. I have completely independent valuations. I want to introduce correlation of Monte Carlo errors. I want to make sure that if the Monte Carlo simulation of stock A is systematically up, because of Monte Carlo error, the Monte Carlo simulation of stock B is going to be up also. Whereas in this case, it could be, it's the opposite. I decouple the errors, so I generate an error in the end, which is comparable to what I'm looking for. Very, very common mistake to anybody who did Monte Carlo for the first time. Very common mistake. Yes?
So I need to be sure that the sequence of random numbers is the same.
Exactly. Exactly. If I need to find generally, if I need to find a difference of things, I have to use the difference of things, the difference of these two things per path. Exactly. I don't need to have one path and then another path with different random numbers and then start comparing. And of course, you know the problem of every sophisticated methodology. I don't care how sophisticated the method is. Garbage in, garbage out. Now, there are a couple of Monte Carlo taboos, I call them. There are things that people who do Monte Carlo for a living, like physicists, they like to discuss, but in the world of finance, they're not necessarily that relevant. You know, how can a computer produce random numbers? Computer is deterministic. Oh, turns out the random numbers are not really random. They are so-called pseudo-random. That's why there are algorithms where you can repeat them. If they were really random, you wouldn't be able to repeat them. Also, how can I be sure that my supposedly uniform distribution is truly uniform? Excel has a uniform distribution. RAND, two parentheses. This is a uniform distribution. In Excel. It will produce a number between 0 and 1 with equal probability. So, these questions are best left unanswered. We assume that Monte Carlo does what it's supposed to do and it does it correctly. Oops. Monte Carlo building blocks. This is what I call the desert island skills. Sometimes we have exercises which are, we're speaking like this. Suppose you're in a desert island. Okay? And we can do one of these. Suppose you're on a desert island. Find the price of a plain vanilla cola. It's impossible that in a desert island you remember Blackett-Scholes. I don't remember Blackett-Scholes. But you still need a price. How would you do it? Okay? Let's look at the basic random number building block. The basic, Monte Carlo building block is the uniform distribution. Okay? It is a function which produces a random number between 0 and 1 with equal probability. Okay? Now, the obvious question is, how come a uniform distribution is relevant when no distribution we discussed up to now in finance is a uniform distribution? We discussed about normal, about log normal, which are basically normal distribution hidden inside exponentials. We may discuss about copulars or student t's or whatever. There is nothing uniform. So how come the humble uniform distribution that you see in Excel can actually help you build a Monte Carlo? The answer is the following. The inverse cumulative of any distribution, the inverse cumulative of a uniform distribution gives back the distribution itself. In other words, if I want to produce normally distributed random numbers, I start with this in Excel. Okay? And I hide it inside the inverse cumulative normal distribution. And this thing produces stuff which is normally distributed. This is the fundamental and cleverest identity you need to know about Monte Carlo. The inverse cumulative of a uniform distribution is the distribution itself. And why is this the case? Very, very short, and again, very tricky and clever proof. Random number, uniform distribution, what does it mean? It produces a number between 0 and 1, uniform. What is the probability that this number is going to be less than 0.6? I'm just saying an example. What's the probability that this number is going to be less than 0.6? It's uniform between 0 and 1.
How many spaces?
It's floating point accuracy, find that. It's uniform between 0 and 1.
100%.
What's the probability that it's between 0 and 1?
100%.
100%. What's the probability that it's between 0 and 0.7? No? 70%. Exactly. It's uniform between 0 and 1. So, since it's uniform, if I have 7/10 of the interval, it has 7/10 probability of falling in, and 3/10 of falling out. So, the probability that the number coming out of the uniform distribution is less than y, say our 0.7, is 0.7, is y. Is this obvious to everyone? You can even try it in Excel if you don't believe it, but it's obvious. If I have half the interval, if say it's between 0 and 0.5, it's 50%, and another 50% of being between 0.5 and 1. Then, what am I saying now? The probability that this thing, the inverse cumulative of the uniform, is less than x, where x is a number between 0 and 1, okay, is the same, now check this out, G here is a probability density distribution, okay? Which means that it's ever increasing. Okay? The probability of something being between minus infinity and 3 is less than the probability of this same something being between minus infinity and 3.1. By what amount? The probability of this being between 3 and 3.1. Okay? So this is a monotonically increasing function. If I say the probability of something, of A, being smaller than B, okay, is exactly the same as the probability I would get if I hit both sides of this inequality with a monotonically increasing function. Obviously, the probability of 2A being smaller than 2B is exactly the same. The probability of A squared being smaller than B squared is exactly the same. If they're monotonic, I can hit both sides. The same monotonic function, same probability. So this is the same as the probability g to the minus 1 of u times, if I hit it with g, is u greater than g